Speaker today is Patrick Adrian from Massachusetts Institute of Technology. Field is plasma physics. Advisor was Johan Frenge. He also did his practicum during the pandemic at Lawrence Livermore National Laboratory in 2021. And again, he did change the title of the talk, so I'm going to have to read it. So studying particle transport using nuclear and X-ray diagnostics of discovery, science, and inertial confinement fusion in Omega and the NIF. So, Patrick, the floor is yours.
Okay, thank you. Hi, I'm Patrick, and I was an SSGF fellow this is the title of my thesis, and so let's get in. First, I'd like to thank many collaborators and sponsors. So these are the collaborators and sponsors for the work I'll present today. It was strong collaboration with Lawrence Livermore, University of Rochester, University of Nevada. However, I've worked on many different projects as a part of my thesis. So today, I'm just going to talk about a more physics-based project, which was studying ion and electron energy exchange in high energy density plasmas. However, different projects that have comprised my thesis work are developing an X-ray imaging spectrometer for diagnosing high energy density plasmas. I've also done some neutron spectroscopy work at the NIF, and also understanding other fundamental plasma physics processes like diffusion in ICF implosions, and also studying laser matter interactions for how we drive capsules. So if any of that interests you, I'd be happy to talk with you after my talk, but today, for the 20 minutes I have, I'll just focus on one of these projects. And I should say also, this diversity of work that I am really excited to have done was enabled by the SSGF fellowship. I wouldn't be able to have worked on so many different projects if it weren't for the freedom that I got from having this fellowship. Okay, so getting into the motivation of my talk. So I'm a high energy density plasma physicist. So one of the main motivations is that high energy density plasmas and ICF codes require really accurate models for different plasma transport processes. The process that I'm interested in today is ion-electron energy exchange. So this is how ions and electrons communicate and exchange energy. And there's a lack of experimental data to validate the different models we have. So yesterday we had a really nice talk from Alex Zylstra about ignition experiments at the NIF. So to the right of the slide here is, as we compress that deuterium-tritium hotspot, it goes up in density and temperature over time. So in the blue kind of dots is a trajectory. So there are different trajectory through density and temperature space. So there are different codes that want to predict, well, how is our plasma going to behave as we compress it and try to achieve ignition. And so recently there's been work to develop new models for how we model ion-electron energy exchange, and there are differences between different theories we implement in the codes. So what we want to do is develop an experimental methodology to test this. So on the plot here, there's contours where there's two different theories for how fast ions and electrons can communicate to each other, and they can differ by 10 to the 30% over the evolution of a NIF hotspot. So in order to get more predictive codes, we need experiments to tell us, well, which model should we implement in our codes. So just to put a little more meat on the bones of this argument, so there are several formulations of what's called in our field the Coulomb logarithm. So for everyone that's not in plasma physics, this is basically a cross-section. So when I say Coulomb logarithm in this talk, that just means what's the cross-section between ions and electrons. And so here to the left, I have a plot of this Coulomb logarithm as a function of densities. So we compress these plasmas to greater than solid densities. And there's a variety of different values for how you would compute this cross-section or logarithm. And the table to the left are the different names of the different theory people who have developed these models, and they get used in various different codes. And so the question is, can we design an experiment to measure these cross-sections? So there are in addition to having different models, there are various different codes used throughout the field of high energy density science. And so if we can provide experiments to better test what's implemented in these various codes, they can become more predictive. Okay, so with that being said, now what I want to move into is the methodology. So the final product of this talk will be experiments measuring this cross-section. So the way we're going to measure this cross-section is that I'm going to describe a novel method based on low-velocity ion stopping power developed by myself and collaborators. So in this plot, what you're seeing is the energy lost as an ion traverses a plasma. So it depends upon that ion's velocity. So there's two different regimes. There's a regime where the ion's velocity is less than the electron thermal velocity, so the electrons are flying around this ion as it traverses through the plasma. If the ion's moving slower compared to the electrons, it will lose energy proportional to its velocity. And it turns out that the constant of proportionality is the ion-electron energy exchange rate, which is proportional to that cross-section. If the ions are faster than the electrons, then the energy loss is proportional to 1 over v squared, and this is like a Coulomb scattering regime. But the regime for which I'm interested in my work is this low-velocity regime, or this what we call below the Bragg peak. So the Bragg peak is when the ion energy loss is maximized, and that happens right when the ions are at about an equal speed to the electrons. The reason we're interested in the low velocity energy regime is because it's directly probing that thermal cross-section between ions and electrons. So the idea here of this method is if we can pass a probe particle through a subject plasma, it will lose energy, and that will encode information about the cross-section. That's kind of the whole idea in a nutshell. So just to make that a little more definitive, to put some equations on the slide. So the idea here is the coefficient for ion-electron stopping power has been shown to be the same as for ion-electron energy exchange. So the rate at which ions lose energy as they move the plasma is fundamentally related to the temperature equilibration between ions and electrons. And I'll note that previous work has used this kind of relationship in simulation codes. So many people who have theories predicting this rate will turn to ab initio simulations to try and validate their models. And this kind of relationship has been used in simulations, but I'm presenting the first kind of experimental use of this technique. So what do we need to measure in an experiment? So to develop the methodology a little bit further, like I said, the energy loss of the ion is proportional to this equilibration rate and its velocity. So in an experiment, what we'll measure is the energy loss. So that's the first measurement we have to make. But then we also have to make measurements of the plasma conditions of whatever plasma we generate. So at the end of the day, kind of in the orange-yellow box, or the yellow box is, if I want to make a measurement of the Coulomb logarithm, which is just basically the cross-section for this interaction, the three kind of measurements I need to make are the energy loss of whatever ions I pass through that plasma, and then I need to make measurements of that plasma density and temperature. So that kind of sets the stage for my experiments. So let's get into that. So the platform we used to study these really high density, high temperature plasmas was using shock-driven D-helium-3, shock-driven implosions filled with D-helium-3 and a trace amount of argon gas with a thin glass shell. And these studies were done at the Omega Laser facility in Rochester. So the reason we fill the capsules with deuterium and helium-3 is that there's the DD and D-helium-3 fusion reactions. Those will generate the probe particles that will pass through the plasma we created, and that will encode the information about the cross-section in the energy loss of these particles as they kind of fly out of our implosion. There's a trace amount of argon in these capsules because that's, as I'll describe, the argon will emit line radiation, which will imprint information about the density and temperature conditions that were reached as we imploded these capsules. And then we chose an implosion platform because that's the only platform that can reach stellar conditions that we want to probe. So we needed to have the spherical implosion platform to reach like gigabars of pressure in these experiments. Okay. And just to relate it back to the methodology, so the specific probe particles that I care about, it will turn out will be the DD triton. So this is the tritium that's produced from the DD fusion reaction, and then the D-helium-3 alpha particle. Those are the particles that will turn out to be the slowest, and they're on below the Bragg peak. The other two particles, of course, important, but these are the two particles that encode the information I care about. Okay, so getting into the experiments, so what we did was the first diagnostic that was critically important was charged particle spectrometers. So as we did the implosion, what happened was, these particles flew out, they lost energy, and we had to measure their energy spectra, and that encoded the energy loss. So what I have here are the 4 different particles generated from the 2 fusion reactions. So to the left are the 2 important ones, which are the DD triton and the D-helium-3 alpha. If we notice, all of these spectra, the energies we measure, they're downshifted from their birth energies. So the birth energy is just given by fundamental nuclear kinematics. That's very well known. And we just measure how much energy they lost. So, and in addition to this, I have a paper about the calibration of these charged particle spectrometers, because that was very important to have accurate measurements of that energy loss in absolute terms. Okay. The next part of this, what I'm cooking here is the Argon line data. So as we imploded these capsules, we saw X-ray emission from argon line transitions. So the idea here is that the widths of these lines we see, so in the left here I kind of have on the y-axis is X-ray energy, on the x-axis is time. So as we did this implosion, which happened over the course of like a nanosecond, we were able to see the fingerprints of the argon. So the idea here is that the widths of these lines are kind of proportional to the density, and the relative heights or intensities of the different lines are proportional to the temperature. So that's kind of how we disentangled the density and temperature. And so what we were able to do was to model those line shapes and compare them to fundamental physics codes, which would predict them and infer the density and temperature as we kind of compressed these capsules. So here to the right, I'm showing the density and temperature evolution of the capsules. And just to say them, the densities we reached in these implosions were something around 10 to the 24 per cubic centimeter in number of electrons. And then the electron temperature we reached is around 1 keV, or 1 to 2 keV, let's say. Okay, so that's how we measured the plasma conditions in time. We also measured the plasma conditions in space. So we had a special diagnostic which was able to image the argon line emissions in different regions of the implosion. And that was really important because, as you can see here, there's different profiles for the density and temperature. So as the capsule implodes, it's not just some uniform medium. There's some spatial profiles to that, to those conditions. And so we had to account that for our modeling of that energy loss. And so what I'm showing here is just the argon line spectra, the data, and some kind of the modeling overlaid on each other from different regions, 1, 2, and 3 of like the implosion core. So for scale, up at the top, the implosions reach a scale of about 140 microns in width. So it's pretty small. Okay, so what the next part of once we have all of that data, we have to synthesize it, and the end synthesis of all the density and energy loss measurements is basically kind of this plot where I'm plotting the energy loss on the y-axis versus the ion velocity. And we've measured the plasma conditions. And so what we're really focusing on is the energy loss of these 2 particles below the Bragg peak, and that's kind of highlighted in this blue box. Because remember, these particles encode information about that Coulomb logarithm or that cross-section. And we want to use basically the slope of this line, to put it simply, to determine what that cross-section is. And then, as I said before, we measured the plasma conditions that relate that cross-section. So for every plasma condition, we can make a measurement of that cross-section. Okay. And then we did a bunch of different experiments which probed different plasma conditions, all the way from 10 to the 23 up to 10 to the 24, and around from 2 to 1.5 to 2.3 keV, let's say. So we were able to vary that. And we did that by changing the drive conditions of the laser. There was also some capsule design changes. just to generate different plasma conditions. And that, as you can see, that had as we changed around, that had a drastic impact on just the energy loss curves. Okay. So we made a whole bunch of measurements of the Coulomb logarithm, or that cross-section. So it turned out that this cross-section is supposed to scale with the Debye length. So in plasma physics, that's the distance, that's the maximum distance in which electrostatic forces can be felt between ions and electrons. And it turns out in these plasmas, the de Broglie wavelength is an important distance scale. So that's the scale at which quantum mechanics becomes important in the interaction between the electrons and the ions. So that kind of sets the max and min scale of this interaction. Thank you, 5 minutes. Okay, and so it turns out that in calculating this cross-section, most theories predicted that this cross-section should depend upon these two numbers, but there was an order unity correction factor that had to account for the collision physics that was going on between the ions and electrons. So the way we chose to model the data was to take our experimental measurements of this Coulomb logarithm and fit them to a form where the C parameter was the fit parameter. So this would tell us this would tell us an experimental inference of this correction factor, which I'll call C. Okay, so getting to the summary. So what was the right C value, I guess is one way to put it. So to the right here, well, first we were able to make measurements of this energy exchange cross-section. We inferred this value of C. So to the right here is the plot of different theories that you might find in high energy density physics code. In the red kind of black point is our data point, comprising all of our, this one point comprises about 12 different experiments. And so we're in a regime where on the x-axis is kind of the electron temperature divided by what's called the Fermi degeneracy energy. And this is kind of telling us how degenerate our plasma is. We're in the non-degenerate regime, so this is the regime where the NIF hotspot is. And we were able to discriminate between different theories to supply which one is the, which one has the experimental support of the evidence. Or sorry, that was, which one is supported, which theory is supported by the experiment. And basically that's being now used in the codes, in different codes in the field. So the measurements were conducted, we probed this plasma regime, like I said, around 10 to the 23 to 10 to the 24, around a few keV. And so now those, these results are now being used to support using these different theories in the codes. So what the kind of summary of my work can be summarized in this plot. So we studied ion stopping power, but also energy exchange. And what I want to show is where my experiments are in relation to the ignition work on the NIF, because that was its fundamental motivation. So the particles we probed on the x-axis, their velocities, like I said, were lower than the Bragg peak velocities. It turns out that that's also true in the alpha stopping problem in the NIF. So as the DT fusion reactions happen, they create alpha particles. Those particles are critical for the self-heating of the plasma, as we learned yesterday. So in the kind of pale red dots is where the alpha particles live at the NIF. On the y-axis is something in plasma physics called the plasma coupling parameter. This just tells you the collisionality of the plasma, essentially. And in the dark red dots are my experiments, and they occupy a very similar space in the collision physics as the alpha particles in the NIF hotspot. So I think we've been able to provide a really critical piece of fundamental physics measuring this cross-section for how those alpha particles will interact with the DT plasma for ignition-relevant experiments. And there's a whole host of other people that have explored different spaces kind of more relevant to alpha particle stopping in the NIF, or in the dense fields surrounding the hotspot. Okay, so I'll wrap up because I got the 5-minute warning, not maybe 5 minutes ago. So we were able to, like I said, validate ion-electron equilibration theories at hotspot relevant conditions. This work I published both technical paper about different diagnostics used on this study, but also the physics paper measuring this property. So that's kind of the conclusions to my physics talk. And I'll just say, like, my last slide is that, the SSGF fellowship enabled me to pursue like novel areas of research. Sorry, I got kind of cut off there. In close collaborations with the national labs. So I published many papers with scientists from Los Alamos, from Livermore, from Sandia. You heard today about ion-electron energy exchange, but I've also worked on developing X-ray imaging diagnostics, and that was really critical to have a collaboration between all three of the labs to test that diagnostic and kind of get it up and running. And I've also had different, as I've collaborated, they've helped me with my projects, and I've helped them with their projects, and that's enabled me to be co-authors on many of their different publications, all the way from the ignition paper, which I'm really happy to be on, to different magnetized implosions and alternative Hall-Raum designs. Like I think it was already said, I did my practicum at Livermore. And then the final conclusion I wanted to say is that, of course, the fellowship has really helped me, but it's also, in doing all of this work, has sponsored or has enabled the next kind of crop of graduate students, both in my group and in different groups, utilize some of the work I've done. So that's been very satisfying to see people, different new scientists using some of the work that was enabled through my fellowship. So thank you. That's my talk.